Hello everyone, in this video we're going to analyze a common drain amplifier. As was discussed, the naming convention goes something like this. You look at where the input is connected in terms of the three terminals of the transistor, and in this case you can clearly see that the input is connected to the gate of the transistor through the decoupling capacitor. And then you look at where the output is connected to, again in terms of the terminals of the transistor, and as you can see the output is connected to the source. So input to the gate, output to the source, and the terminal that is neither connected to input nor to the output is called the common terminal. So therefore this configuration is a common drain amplifier. That said, let's start analyzing the circuit. So in this specific case, the transistor is actually biased through an ideal current source, and therefore we don't really have to do anything in order to calculate the bias, because the bias current of the transistor is obviously equal to the current of the current source, which happens to be given as 5 milliamp. Let me rewrite this value right here. So that would be 5 milliamp. Now, with that realization, we can actually proceed to develop the small signal model of the circuit. So I'm going to redraw that circuit right here. We're going to start with the input, and the capacitor is obviously a short circuit, and then we have the 500k resistor between the gate and ground, and this is right where the small signal model of the transistor is going to be. And I actually have the small signal model just drawn here. So gate, drain, and the source. Now notice that in this question lambda is not 0, and therefore the model is going to, in the output or in the drain, is going to have both a dependent current source in parallel with a resistor, and that resistor is called R0, and the value of that resistor is calculated using this equation: 1 over lambda, which is non-zero, times the bias current of the transistor. So we're gonna use that, and we can obviously develop the values for both GM and R0 of the small signal model. And then in the drain you have the 5 volt, and therefore that gets directly connected to ground. As we discussed, all the DC voltages are going to be turned off in a small signal analysis, and that means for a voltage source you're going to connect that to a ground, short circuit that to a ground. And then in a source, now you're going to have to again turn off the current source as well, because that's also a DC value, and then turning off a current source is equivalent to making the current equal to 0, which is the same as opening the circuit up. So in this branch of the circuit you get an open circuit, but right here you have a capacitor, so that's a short circuit, and then gets connected to the 4K and then the ground. So that would be your 4K, that's the 500K, this is VI, and right here this would be your V out. Now again, this is your R0, and this is GM VGS. I'm going to leave the value of R0 and GM VGS here, and then we can later go back and calculate that. So now with this small signal model we can start analyzing the circuit. So this is one of your nodes. This is the output node, and this is obviously your ground. And we have a current here, no current there, so that's 0. And then we have one current here. I'm going to call that, obviously I can call it I load, for example. And then we have a current here. So I'm going to current through the resist. There's a current through the R0. I'm going to call that I naught. And obviously the current passing through the current source is GM-VGS. So before doing anything, let's just make sure that we have a clear, well, when I'm doing the, when I did chose this node, I could have done a better job, because this is all one node. This is all one node. Now therefore you can clearly see that I can write a KCL over there when I start writing the equations. So KCL for that node, and the only node that I can write KCL for, or I need to write KCL for, we have GM-VGS going into that node, so GM-VGS, and that's equal to IL plus I naught. Now before I proceed, I'm going to actually basically define what VGS is in my circuit, because in the model VGS is a general term, and depending on your way of labeling the circuit, VGS might need to be rewritten based on the variables in the circuit. So that's VG minus VS, and in our labeling, VG is equal to VI and VS is our V out. So I'm going to rewrite the same KCL knowing what VGS is. So that would be GM times VI minus V out is equal to IL plus I naught. Now I'm going to move on to writing equations for components. So we have basically this current, this resistor and that resistor, for which I need to write the equation for. I can actually write the equation for the 500K, but that's not really required unless you want to know what the current, small signal current through that 500K resistor is. So for the 4K, IL is equal to V out divided by 4. And for R naught, we have I naught is equal to V out divided by R naught. So from these three equations, we have what we need in order to write, find out what the gain for the transistor for this amplifier is. So from these three, we have GM VI minus V out equal to V out divided by 4 plus V out divided by R naught. So this equation only has VI and V naught in it, so we can certainly find the gain. GM-VI is equal to V out times GM plus 1 over 4 plus 1 over R naught, and therefore V out over VI, which is the gain of the amplifier, is equal to GM over GM plus 1 over 4 plus 1 over R naught. And you can basically at this point either simplify this or just leave it as is. So this is the gain for the amplifier. Now, in order to calculate the value for the R0 and GM, we can simply use these equations. So R0 would be equal to 1 over lambda, which is 0.02, times ID, the current, which is just 5 milliamp. I'm going to use milliamp, and then the resistance would be in kilo ohm. So that is equal to 10 kilo ohm. And then finally GM would be 2 times the square root of Kn, which is 1 milliamp per volt squared, times ID, which is 5. So that would be 2 square root of 5. So with that, we put values in this equation and we have the gain of the amplifier. Now, in order to fully analyze the amplifier and calculate all the important characteristics associated with the amplifier, beyond the gain, there are 2 other parameters that are usually important, and those are the input resistance and the output resistance for the amplifier. So for the input resistance, it's actually pretty easy to see what the input resistance is. Looking in from here, obviously the only resistance that you see is the 500K, so the input resistance is just simply 500K. Now looking in the output, when we look at the output, so this is where you look at the input and this is where you look at the output. When you look at the output, you actually you should not include the load resistance in order to calculate the output resistance of your amplifier. In other words, when the output resistance is calculated, the load is removed and you put a load right here and a source right here, and look at the current that is coming out of the source, and then take the voltage of that source and divide that by the current. And in the process of doing that, you're actually turning off any other source that is connected to your circuit. And once you do that, you can clearly realize that after writing all the equations, you're going to see that the output resistance in this circuit is simply R0 in parallel with 1 over GM. So output resistance, I'm going to write these here. So input resistance Ri is just simply 500K, and the output resistance is equal to R0 in parallel with 1 over GM. And when you do the calculation and put values, you will realize that obviously you can see that here too, that 1 over GM is much smaller than R0. So this is, you can estimate this to be very close to 1 over GM. So with this, our analysis of the amplifier is complete. Now, one thing that I want to mention here is that obviously when you look at the gain equation, it's clear that this gain is smaller than 1, because you're dividing GM by something that obviously is larger than GM. And that's true for all the common drain amplifiers. So in a common drain configuration, your gain is something smaller than 1. So then the question becomes, why would you use a common drain amplifier? Now, when we discussed characteristic of an amplifier, we mentioned that there are 3 important characteristics. And for a good voltage amplifier, you look for a very high gain, which is one of the characteristics of an amplifier, but also there is input resistance and output resistance. And a good voltage amplifier has to have a really large input resistance and very small output resistance. Now, if you look at the input resistance and output resistance in this question, you can clearly see that the input resistance is very large and the output resistance is a small number. By the way, this is in kilo ohm. because everything was in milliamp, all the currents were in milliamp, so 1/GM would be in kilo ohm. All the resistors are in kilo ohm. So it's, when you put this number here, is going to be in the range of 220-ish ohm. So with this, you can basically see that you can design a common drain amplifier to have a large input resistance and a small output resistance. And that's why this configuration is useful, because even though that you don't get a large gain, it's basically a gain that is smaller than 1, but you can get a large input resistance and a small output resistance, and therefore you can combine this into a hybrid amplifier design where you have different stages of amplification, so that you get the gain from one stage and then you get, say, the large input resistance or small output resistance with a stage like this, depending on where you're going to put it. This a common drain actually is quite commonly used in the output of a multi-stage amplifier in order to achieve a small output resistance, which roughly is about 1/GM of the transistor that is in the output. Hopefully this has been useful, and thank you for your attention.